Hey everyone, and welcome back for part 2 of chapter 8 on bivariate correlations. In this section, we are going to focus on how we interrogate association claims, basically how we make judgments about the validity of an association claim, whether we are going to accept this claim as a good claim, or whether we might find some problems, or how we might find some problems with particular association claims. So the first thing we need to do is sort of think about our validities. We are going, when someone makes a claim about an association, that variable X is related to variable Y, we can ask a few questions like construct validity. How well was each variable measured? Because if you don't measure your variables correctly, then who cares about your claim, right? If the measurement is bad, then the claim is bad. Statistical validity. How well do the data support the conclusion? And here that we're going to bring back our discussion about basically the size of correlations, the whether something is a small, moderate, or strong correlation. Internal validity, which is the idea that we can or cannot make a causal inference about something. And we're going to talk about, we're going to dive a little more specifically into reasons why we don't like to make causal inferences from associations. So we're gonna find that association claims lack internal validity. They can have construct validity, they can have statistical validity, but they are generally not going to have internal validity. We'll talk about why. And then we want to examine external validity. To whom can this association be generalized? So we'll start with construct. Basically, how well did we measure each variable? Does that measurement have good reliability? Does it have our face validity, concurrent validity, discriminant or convergent validity? Do we have, if this is a rating, do we have an inter-rater reliability to look at to assess the degree to which raters are converging on similar answers and similar scores? Basically, we want to evaluate all of those questions that we've seen in the measurement chapter to make sure that our measurements of our variables are good. Because remember, in an association claim, we have two variables, right, X and Y, and we're not manipulating anything. All we're doing is measuring the variables. So the important part of construct validity for an association claim is measurement, because our variables are measured variables. They are not manipulated variables. They are measured continuous variables. So if our measurement is bad, if the reliability of our measurement is bad, if there's no discriminant or face or validity or inter-rater reliability, then we have a problem with potentially with our measurement. And if we find that construct validity is lacking, then maybe we don't put much stock into that claim. So, for example, I think an example I used in part 1 was GPA being related to income after graduation. So imagine that our measurement of income was simply to ask people, how much money do you make? That's an okay measurement of income, but it's not perfect. People are going to lie. People might get it wrong, right? How easy would it be to confuse? Well, are you talking about my salary, right, for a year? Are you talking about how much money I actually take home at the end of the month, right, after taxes and withholding and healthcare, right? Are you talking about how many dollars get direct deposited into my account, or are you talking about the contracted salary that I have, right? It can be a little bit ambiguous. What about people who are employed hourly, who might vary across the month or the year and how much money they make? So it's difficult for them to predict their income. Maybe on a week when you get a bunch of overtime and you're making time and a half, your income looks a lot higher than other weeks or other months. So if we simply ask people their income, then we might say that we have a construct validity issue with one of our measurements. And we would prefer that income be measured by looking at tax returns, or that income be measured by some sort of statement from your employer, right? Something that's more valid than simply asking people their income. So the next interrogation we want to do is statistical validity. How well do the data support the conclusion? Here we want to ask a few questions, that some of which we have approached and some of which we will approach, and you'll get a little bit more in depth with some of this in the next section when you do hypothesis testing with correlations. But we want to assess what is the effect size, right? The magnitude of the effect. This is small, medium, large correlation. Is the correlation statistically significant? That's what you're going to get into in the next section with hypothesis testing. Might there be outliers affecting the association? We'll talk about what that means. And then, do we have some funny situations that can occur with an association, a claim, and a correlation? Mainly restriction of range, meaning you have some potentially either floor or ceiling effect. If you think back to our chapter on measurement, if we have a floor or a ceiling effect, I guess I should be going like this. If we have a floor or a ceiling effect, it can restrict the range of possible values for one of your variables. And that's bad for a correlation, because a correlation depends upon variability in the variables in order to make an assessment of how changes in one variable, or variability in one variable, is associated with variability in the other variable. So if you restrict the range of a score, then you can have problems having enough variability to make an appropriate assessment with our correlation. And then lastly, is the association curvilinear? This refers to non-linear relationships. So when we do a correlation, we assume that the relationship between the two variables is linear, meaning it can be described as a straight line. However, not all relationships are best described as straight lines. Some relationships are like parabolic, right? They're parabolas. Some relationships look like steps, right? They're not described best as a straight line. They go up and then they plateau. Then they go up, then they plateau. So we want to be on the lookout for curvilinear relationships, because that is bad for a correlation. We would need a different statistical test to assess for curvilinearity. So, effect size. This is the discussion we had in part 1 about the strength of a correlation. So this one on the bottom, we would say, is stronger than the one on top, because there's less spread around the line of best fit. There's less ambiguity. This one on top is a weaker correlation because it's messier. There's more ambiguity here. So in essence, what's happening when the math is done for a correlation coefficient, basically what's happening is you're comparing the distances of each data point from the line of best fit. So the line of best fit is the point, is the line that reduces these distances to the lowest point possible. But then what makes a strong correlation is that those distances are very small, meaning that the points, the data points, are very close on aggregate to the line. What makes for a weak correlation, or a smaller effect size, is that even though this is the line of best fit, it still doesn't fit great, right? It's the best we can do, but it's still not very good. There's still lots of distance from the line to the data points, which means it's a weak relationship. So the line of best fit is the best line possible, but some best lines are better than other best lines, right? So both of these lines are the best line possible given the data, but the one on the left is a much better representation of the data, right? There's less error going on. Whereas the line on the right is, even though it's the best you can do with these data, it's still not great because there's lots of error. And that just means that these two variables have a weaker relationship and these two variables have a stronger relationship. And in fact, this makes sense with these variables. On the y-axis, we have height of adult male at age 18. And on the x-axis of this scatter plot on the left, we have that male's height at age 2. So we can see that if you're tall at age 2, you're probably going to be a tall adult. If you're, average at age 2, you're going to be an average adult. If you're on the short side at age 2, you're going to be on the short side as an adult. There's a very strong and clear relationship between height at age 2 and then height at age 18. And this is actually kind of what you do when you have a kid. When you have a boy, you tend to be able to predict their height at age 2. Girls develop a little faster physically, and so you can predict their height at age 1.5 at 18 months. Over here on the right, with the weaker correlation, we still have the adult age 18 adult male height on the y-axis, and here we have the mother's height on the x-axis. So mom's height matters, right? There is a positive correlation here. It's just weak, right? You can have someone with a very short mom who ends up being tall. You can have someone with a very tall mom who ends up being short. Right? Mom's height is a weak predictor of son's height, but son's height at age 2 is a better predictor of his own height at age 18 than his mother's height. So again, is the correlation statistically significant? You're going to go over that in the next section, in the next lecture, hypothesis testing with correlations. So we're going to skip that for now. Additionally, outliers, restriction of range, and curvilinear relationships will be discussed along with hypothesis testing. So we're going to jump to internal validity. Can we make a causal inference from an association? We're going to spend a little bit of time with this and really break down why association claims cannot be causal claims. So if you remember back to, at this point, a few modules ago, to our 3 causal criteria, in order to make a causal claim, we must satisfy 3 conditions. The first, covariance. Basically, the variables have to be correlated. They have to co-vary with each other. They have to be related mathematically. That's step 1. We cannot claim that A causes B unless they have a statistical relationship. Causal criteria number 2 is we need temporal precedence. We need to be able to say that if A causes B, A must precede B in time. The thing doing the causing must come first. Pretty straightforward. And our third causal criteria is, do we have internal validity? Is there some outside, unknown, third, fourth, or fifth variable impacting our relationship here, such that we might be thinking that A is causing B, but actually what's happening is that variable C is exerting a dual influence onto A and onto B simultaneously, such that it makes it look like A and B are related to one another. This is our example of ice cream crime and temperature. So A might be ice cream sales, B could be crime, and it looks like ice cream sales and crime are related to one another, that maybe for some wacky reason, people buying ice cream makes them commit crimes, because there's a relationship there. But really what's happening is temperature is over here in the side, temperature is exerting an influence on both of those variables. So temperature is causing the change in ice cream sales, and temperature is simultaneously causing the change in crime. And so it just looks like ice cream and crime have a causal relationship, even though they don't. They simply have an association. Now, often in association claims and with bivariate correlational studies, we're going to satisfy criteria one, right? If there's a statistical relationship, check, right? We have covariance. Oftentimes, you'll be able to satisfy criteria number two. Sometimes you will, sometimes you won't, but it would not be uncommon for a bivariate correlational study to also satisfy criteria two. This one is satisfied sometimes and not other times by association claims. What association claims and bivariate correlations generally lack is internal validity, the ability for us to state and claim that there are no other variables exerting influence. Because in a bivariate correlational study where we simply measure already existing behavior, we have not controlled anything, we have not manipulated anything, we haven't done any work other than basically asking people questions, for example, right? What's your GPA? How much money do you make? We just ask them in a survey. We didn't do an experiment, right? We did research, but we didn't do an experiment where we actively manipulate some variables and control other variables. And so because of that, we do not achieve internal validity in association claims. Because there could always be that lurking variable that we didn't control for, or that we didn't measure, or that we didn't manipulate. So as an example, let's talk about this. Here we have a scatter plot of self-esteem on the y-axis and height on the x-axis. Let's think about our three criteria and see if we can identify which of the three criteria we meet. So take 20 seconds and think about it really quickly. So in this example, it looks like we meet criteria one. There is a relationship between height and self-esteem. In general, the greater your height, the higher your self-esteem, right? We have maybe a moderate positive correlation here. We would draw our line of best fit kind of like this. The relationship is pretty clear, but there's some variability. There's some messiness around that line. So maybe we have a moderate positive correlation. So check, right? We have covariance. Temporal precedence. Can we establish whether height or self-esteem precedes the other one in time? I don't think so. It doesn't seem like we can do that. I can't say your height came before your self-esteem, or your self-esteem came before your height. Right? It can't be done with these variables. We cannot establish temporal precedence. And so we fail criteria two. And of course, we also fail criteria three because there's a myriad of other variables that could be influencing both of these. So I don't know, just one quick example, genetics. We know that genetics are going to help determine your height. And it would make perfect sense if there is a genetic component to your self-esteem as well. It's not that height is causing your self-esteem. It's that you have particular genetics that might predispose you to height and self-esteem, something like that. What if, I don't know, tall people have good self-esteem because tall people tend to be recruited to play sports in college, and that makes them feel good. I don't know, right? If you're tall, you're more likely to play basketball, volleyball, football, whatever, right? I don't know. Dumb example. But the point being that there's all kinds of other stuff that could be impacting both height and self-esteem. And so we fail the third criteria because we didn't do anything to control or manipulate any of those other variables. So we cannot make a causal claim. We have number one, but we do not have criteria 2 and 3. And lastly, let's discuss external validity with association claims. To whom can our association be generalized? So the first question you have to ask yourself, as we discussed previously, is do you even care about external validity? You're allowed to not care about it. You just have to justify not caring about it. Ideally, we want our result to be as externally valid as possible because the idea being that we want our research to inform and help as many people as possible, right? We want it to be as externally valid as it can be or as it needs to be. But it doesn't have to be infinitely externally valid. So you need to ask yourself the question, how externally valid is this claim trying to be? Are we making a claim, right? This claim between height and self-esteem seems to be making a claim about like all humans, right? That's a really, really externally valid claim. That's a high benchmark to clear. So if this claim is being made about all humans, and then we need to ask questions like, what was the sampling method? What was the gender, the age, the ethnic background of the participants, right? We need to know who are the participants and how did we find them so that we can make a decision about how externally valid. Does this actually apply to all humans? Or is this, were these data collected, with, I don't know, only middle school female athletes, right? Or something like that, right? So these data were actually exclusively female middle school athletes. That changes external validity. But maybe you're a developmental psychologist who studies gender and self-esteem. And so you actually don't give a shit about drawing conclusions about male self-esteem. All that this is only focused on female self-esteem. So you don't care if it's externally valid to males. The purpose was to examine female height and self-esteem. That would be okay. You would just have to make the argument, or the claim would have to make the argument for why that matters. And then the methods would have to match up with that claim. So is it important? But then also, do we have any moderating variables? And moderating variables, we're going to define, don't worry, can actually impact external validity. So, sorry, this kind of runs over right here. External validity and moderating variables. A moderating variable is a third variable that changes the relationship between the other two variables. So, I want you to look at this graph over here on the right, this scatter plot. On the y-axis, we have multitasking test score. So how good are you at multitasking? Versus time spent multitasking, how often you multitask. And then we have actually a third variable represented here, and it's age. So all of the Y's are data points for young individuals, young adults. All of the O's are data points for older adults. So what I want us to notice is that If we look at just the young adults and just the older adults, then they seem to have similar relationships, right? They have a negative um, correlation, an inverse relationship. But take a step back. I want you to imagine that the O's and the Y's are all just data points, right? We did not distinguish between older and young adults. If you drew your line of best fit, it would kind of be going the other direction, right? It looks like a positive relationship if we treat all of these data points as the same, right? As coming from just humans, the same group. Then the nature of the relationship is different. So the relationship between multitasking score and time spent multitasking is dependent upon age. When we include age, it changes the relationship to a negative one within each of those age brackets. So what's happening is that we can claim external validity because the relationship is the same for young adults and older adults, even if the relationship doesn't quite look like that for if we combine them, right? So here we can claim that the result is valid for both young adults and older adults because they have the same negative relationship. So a moderator is a variable that can change the relationship between the two variables that were originally correlated with one another. And it can change it even more dramatically than you might think. It can move you from a relationship to no relationship. So the relationship we're going to look at is sport team success and attendance. So we gather data on how successful a city's sports teams are, and we compared it to their attendance. You might expect that the better the sports teams in a city, the more attendance to those sports teams. That would make logical sense, right? And if we look at Phoenix, Arizona, that's the case. It's a moderate correlation, right? 0.29. That's close to our 0.3 for moderate. So we can say that in Phoenix, Arizona, sport team success has a positive relationship with attendance. The more successful the team, the more attendance to the games. However, if we look at Pittsburgh, Pennsylvania, there's actually a negative correlation. It's a weak negative correlation, but it's there. It's a negative correlation between sport team success and attendance, meaning the more successful a team, the lower the attendance. What's happening here is that these cities differ on a very important variable called residential mobility. Basically, how easy is it for the residents of a city to move about their city? How many people have cars? Do they have a good public transportation system? Is there a subway? Are there buses? How mobile is this city? And so Phoenix is categorized as a high mobility city, meaning it's easy for people to move around the city. Pittsburgh is a low mobility city. It's difficult for people to move around Pittsburgh. I've been there a couple times. It's kind of a hot mess of a city. It's a cool place. It's fun, but there's not any good public transportation. The city is built sort of like in some mountains where like three rivers come in together. There's like bridges everywhere. It's very confusing. It's not a very mobile city. And so the mobility of a city changes the nature of the relationship between success and attendance, where people who can easily move around the city are more willing to go attend the games if their team is successful. But people who cannot move around a city have a weaker relationship between those two variables. It doesn't matter as much to them. So this third variable, residential mobility, is changing the relationship between our original two variables of interest, success and attendance. So Arizona, Phoenix, Arizona might look like this, right? A winning percentage on the x-axis, attendance on the y-axis. It's a, weak to moderate positive correlation, whereas Pittsburgh is going the other direction, right? You'd be forgiven for maybe describing this as no correlation, or it's a very weak negative correlation. And so you can see that even though we're looking at the same two variables, attendance and wins, we have different relationships based on the city that we choose, which means that this finding is not externally valid. It doesn't apply to everyone. It only applies in cities with high residential mobility. Cities with low residential mobility do not have the same relationship. The association does not apply to them. So when looking at moderations, you can kind of think of moderations as situations where if we divide our sample along some variable, right, like city or young versus old, then that dividing third variable is going to create different lines of best fit. So here we have two variables, blood pressure and carrots consumed. For older adults, the more carrots you consume, the lower your blood pressure, right? Awesome. I don't know if that's true, by the way. Don't just start eating carrots because this stupid example said to. This is not health advice. Please don't take it as such. Older adults who eat more carrots have lower blood pressure. So we have a negative correlation. Whereas for younger adults, we have a different relationship. It's sort of a positive relationship. Notice that if you sort of average these together, right, if we combined the younger and older adults, we'd basically end up with no relationship, right? It'd be our flat horizontal line of no relationship. But when we split the sample into young versus old, we get a relationship, which means that age moderates the relationship between blood pressure and carrots consumed, such that the addition of the third variable age changes the nature of the relationship. And so this means that our finding has limits to its external validity. It is less externally valid than you would think if you did not include age. So we're going to go over this idea more in a couple topics when we talk about multiple regression or multivariable relationships. But I want to really quickly distinguish between a moderator, which changes the relationship between two variables, and a third variable, which accounts for the relationship between two variables. I'm not going to spend too much time on this because you're going to get more time with it in a later section. But I want you to imagine that we observe a correlation between class attendance and GPA. Right? We have a positive correlation. The more you attend class, the higher your GPA. Positive correlation between class attendance and GPA. It's possible that attending class doesn't actually have anything to do with your GPA. What's actually happening is that motivation is exerting an impact on both of these variables simultaneously. So motivated students attend class and motivated students get good grades. Attendance doesn't cause you to get good grades. Motivation is accounting for the relationship between attendance and GPA. So when a third variable accounts for the relationship, we can think of it right now as a third variable versus a moderator, which doesn't account for the relationship. It changes the relationship between two variables. So the addition of age doesn't account for the relationship. It qualitatively changes the nature of the relationship between blood pressure and carrots consumed, where one group, the younger adults, has a positive relationship, and one group, the older adults, has a negative relationship. So moderating variables change relationships. Third variables account for relationships. So a moderation example of this idea, so attendance and GPA, might be gender, right? Where maybe women have a very strong positive relationship between attendance and GPA, and men do not, right? So if this was the case, then we could say gender is moderating the relationship between attendance and GPA, because for women, the relationship looks one way, and for men, the relationship looks a different way. Gender doesn't account for the relationship. Gender changes the relationship. So that's a moderator. When something accounts for the relationship, it's a third variable. We're actually going to call this a mediator. It's a mediation. But that's later. Okay. So that's it for this section on Chapter 8, bivariate correlations. I want us just to do a little bit of practice. I have 3 examples of association claims. And I want you to think about whether these claims are positive or negative. I want you to provide an explanation for the correlation, like what could be happening, what could be a mechanism that explains this relationship. Then I want you to come up with a potential third variable that might explain the relationship, so a mediator, as we just said. And then I want you to come up with a potential moderator that might change the relationship. So there aren't really correct answers to B, C, and D. There are only correct answers to A, right? B, C, and D are meant just to have you think about the nature of relationships and associations. What could be going on? What are potential third variables? What are potential moderators? Because, especially with human behavior, things are messy. Things are difficult to explain. There are often multiple variables needed to fully explain a relationship. So I want you to press pause, go through all 3 of these, see if you can come up with answers to A, B, C, and D for each one. I'm going to, in like 20 seconds, I'm going to tell you the answers for A, but keep in mind, B, C, and D don't have any right or wrong answers. It's more just to get you thinking. So use it as an opportunity to sort of explore the nature of these relationships. So go ahead and press pause, do this little activity, press play, and I'll tell you the answers to A. Okay, so I hope you're back. Really quickly, let's identify whether these are positive or negative. A government study reveals that the more mothers smoke, the more her children are likely to exhibit behavioral problems. So our key here is more smoke, more behavior problems. So they're moving in the same direction. So that's a positive correlation. Number 2, researchers investigating relationship between alcohol and memory found higher doses of alcohol are associated with lower scores on a test of memory recall. So high alcohol, low memory. So that's an inverse relationship. They're moving opposite of each other. So that's a negative correlation. And lastly, a survey of adolescents noted those who watched the most TV during the week received the lowest ratings on a measure of general health. So the most TV, right? So the more TV you watch, the lower your ratings on health. It's an inverse relationship. They move in opposite directions. And so we have another negative correlation. Again, there are no really right or wrong answers for B, C, and D necessarily. just use them to flex your muscles about understanding the complexity of association claims. So thanks, everybody. Hope you enjoyed the lecture, and I will see you next time.